So hi, everybody. I'm going to talk today about my work over the last roughly 10 years at this point on building extremely tiny, very low-cost satellites, and kind of where that's all taken us over the last decade. So first, I'd like to open with a question that I'd like to pose to all of you, and kind of try to get you thinking about this while I go through the talk, and hopefully we can revisit this at the end during the Q&A. What if flying a satellite costs less than your smartphone? I think this is a really interesting and kind of deep question that really gets at both how ubiquitous satellite data is in our everyday lives, everything from weather forecasting to GPS navigation to timekeeping that runs the power grid, and also how expensive it is to fly things in space traditionally. And yeah, so I think I'd like to kind of have us ponder this question. And I'll just to kind of go through some of these things, talk about some of the things I would do. So first, maybe not so well known, is that the second largest consumer of satellite-based data is actually the ag industry. I was super surprised when I first learned this a number of years ago, but it turns out the modern ag industry in America in particular relies heavily on satellite-based imagery, and in particular hyperspectral imagery that captures bands outside the visual into like the infrared. And what ag companies are doing with this data is actually they're able to extract things like soil moisture and various crop health metrics from this kind of image data, and target application of watering and fertilizer down to like the square meter level in their crops. So this has been a huge boon to the ag industry and has increased crop yields and reduced water consumption. But so far, the cost of this data and the analytics required to do all this is cost prohibitive, such that it's only being done in first world countries and not in places that perhaps could benefit from this sort of technology the most. So one of the things I might think about doing if we had very low cost satellites is bringing down the cost of this data to help agriculture and say in the developing world. Another one is weather forecasting, like I mentioned. Turns out some of the best data for forecasting the weather comes from a measurement technique called GPS occultations, where you sort of catch GPS signals that graze through the atmosphere. In order to do this, though, you need a receiver on a satellite in low Earth orbit, and you need to have just the right geometry happen between that receiver satellite and one of the GPS satellites. And this is kind of a random occurrence that happens, every so often, maybe a handful of times a day. And right now, we just don't have enough of these receivers in space to get the kind of data we would like to better calibrate weather forecasting models. And we have lots of cheap satellites. You can imagine dramatically improving our weather forecasting capabilities. Another one is disaster response. These are two really amazing images captured by a small satellite startup called Planet Labs. The first one is a picture of a tornado. The street going across the image is actually the path of a tornado in Wyoming last year. And the one on the right is of Kathmandu after the big Nepal earthquake a couple of years ago. In both cases, the satellite basically got lucky and happened to be overhead either during, in the case of the tornado, or immediately after, in the case of the earthquake, these natural disaster events, and got these kind of lucky shots. But generally speaking, even with the kind of emergence of low-cost, smaller, cheaper satellites in recent years, the maximum, kind of best case revisit times, which is how frequently the satellite will come over the same spot on the ground for even very large constellations, is maybe once a day in the best case. And so if we had smaller, cheaper, larger numbers of these kind of small, cheap satellites, you can imagine having almost continuous coverage blanketing the Earth to capture these kind of events in real time, target first responders and that sort of thing. Another one that's actually quite near and dear to me, going back to when I first got into this as a grad student, is wildlife conservation. This is a picture from the Cornell Lab of Ornithology. These are collaborators of mine when I was a PhD student. They've developed some of the smallest electronic radio tracking tags in the world for tracking migratory bird species. This is challenging because these birds can only lift oftentimes a fraction of a gram before the tag becomes too heavy for them to fly. And the other thing that makes this hard is that these birds, many of the species migrate all around the world, like halfway around the world from pole to pole, twice a year. So really ground-based tracking systems can't keep up with them. And we fundamentally need to do this from space so that we can get this kind of global perspective. And this sort of data has huge implications for climate change and conservation efforts. So this is yet another thing where smaller, cheaper satellites can provide really interesting and insightful data in kind of an Earth-facing context. And the final one, being a space nerd, is space exploration applications. This is obviously something I've been into since I was a little kid, but things that we've looked at in the context of these ultra small, ultra cheap satellites are things like raining down a swarm of very small, say almost disposable satellites into the atmosphere of another planet to study the atmosphere in a way that would only be possible if these satellites were effectively disposable. And another thing that's gotten some attention is studying the gravitational fields and by extension, the internal composition of asteroids by sort of flinging a whole swarm of these very small disposable satellites in the path of an asteroid and watching the gravitational tug of the asteroid on these small satellites as they pass very close, and we kind of don't worry about or don't care about them potentially colliding because they're essentially disposable. Okay, so here's some ideas on the continuum from near term to crazy and longer term. And so now I'd like to kind of switch gears a bit and tell you what I and several collaborators and my graduate students have been up to in this general area of super small, low-cost satellites. So this is a picture of a satellite that I developed as a graduate student that we call the Sprite. And this is a couple iterations in, but this is state-of-the-art as of a few years ago. We've kind of taken this one step further beyond what you see here. This is a single printed circuit board. It's about 3.5 by 3.5 centimeters and weighs 3 or 4 grams. And what's on here is a solar cell, a microcontroller, a radio transceiver, and kind of whatever sensor payloads you can fit. So in this case, we have a gyroscope and a magnetometer. We've put all kinds of other sensors on these, but basically anything that you can buy on DigiKey that fits on an IC that we can put on the board, we can have a large range of sensors on these things. That's it, more or less. There's no energy storage. These just run whenever they're in the sun, and there's nothing else. This is the satellite. This is what we fly in space. The kind of main driver behind this is kind of the thought experiment of how small and how cheap can we make a spacecraft. So these are about $50 or so to make in small quantities. The most expensive part of the solar cells. Those are actually the only space-rated component on the whole board. They're triple junction gallium arsenide, so high efficiency solar cells that are typically used on satellites. Everything else is COTS stuff that's in smartphones and car key fobs and this kind of thing that we get on DigiKey. I should mention also the solar cells are kind of interesting. Notice these are actually 2 triangular cells. They're kind of the trimmings that are left over from when they cut large square cells out of round wafers when they make these high efficiency cells. And we were able to get the kind of off trimmings from one of the fabs for very low cost, and then kind of cherry pick the good ones. Okay, so this is kind of what we're talking about when we say chip satellite or femto satellite. And now I'll talk about a bit about our efforts at actually flying these in space. So this is the first time we ever flew something like this in space. This is now going back almost 10 years to an ISS experiment called MISSY 8, which is a material science experiment that flew on the outside of the space station. These are just fantastic pictures that I can't help share when I give these kind of talks. This is the MISSY 8 experiment over here, this big aluminum box, basically. And this is a picture taken out the window of what's called the cupola on the ISS of these 2 astronauts doing a spacewalk to install this experiment. And you'll notice maybe that the astronaut on the left here is actually holding a camera and taking another picture. This is the second astronaut installing the device, taking another picture of the installed experiment. So it's a picture of someone taking a picture of someone taking a picture of the experiment. And here's our 3 little prototype chipset boards out there in space on the outside of the ISS. This was actually a material science experiment that we managed to get on at the last minute because another experimenter had pulled out. And my advisor got a phone call saying, hey, we have this space on this experiment. Is there anything you want to fly? Oh, by the way, we need it in 48 hours. So this prompted, crazy sleepless couple of nights to get these built up and potted in epoxy and all this kind of stuff, and then driven down to Naval Research Labs to get it installed on the experiment. So this went up on actually the second to last space shuttle mission, STS-134, and we actually physically got them back about 3 years later. And sure enough, we brought them in the lab. They're a little worse for wear. You can see what actually happened here is the epoxy encapsulant we put these in ended up darkening under UV exposure, which we didn't know about at the time we chose that epoxy, and probably impacted the solar cell performance a bit. But sure enough, we got these back, put them under a lamp in the lab, and they powered up and started transmitting right away. So it kind of gave us some confidence that these COTS electronics could actually survive in this radiation environment in low Earth orbit. I should mention also that unfortunately we couldn't get any signals from these while they were on orbit, because this whole experiment is located on what's called the anti-nadir side of the space station, meaning this is out into space and Earth is down here in the lower left. So there's a big hunk of space station between us and them, and the signals unfortunately couldn't be received back on Earth. So this is our first foray into flying these kind of little satellites. After this experiment, I kind of got this idea, kind of decided, well, okay, we kind of proven that these things can work in space, the electronics can survive. Let's actually now go and try to fly them as free-flying spacecraft, as real satellites. So this idea was hatched. The idea here is to deploy sort of a swarm of these tiny chipsats out of a mothership satellite. This mothership satellite you see here is something called a CubeSat. This has become kind of widely used standard for small satellites now. The one here is something called a 3U CubeSat. So it's made up of 3 of these units, which are 10 by 10 by 10 centimeters and about a kilogram. And so you can have a 1U, 2U, 3U, and now 6U and even larger versions of these CubeSats. They have a standardized interface to launch vehicles and a whole ICD and testing requirements that are totally standardized, which has really opened up access to space for small startup companies and universities, because you can build to the spec for these CubeSats and then go out and find ride share opportunities where you can tag along on to bigger satellites, and everyone kind of knows how to accommodate these because they're all standardized. So we decided, to build the mothership into one of these CubeSats so that we could easily go shop around for a launch for it, and deploy roughly 100 of our little chipsats out of this CubeSat mothership in low Earth orbit. Okay, so KickSat, sort of a evocative name for a couple of reasons. One of the reasons is that as a sort of starving PhD student, I didn't have any money to do this, and actually Kickstarter funded my satellite mission as a PhD student. Put this up on Kickstarter. We raised about $75,000, which was enough to build all the hardware for this. And you might ask what people got for their dollars. We did a bunch of things, including laser engraving backers' names and messages on the side of the spacecraft structure for the CubeSat. We also sent people development kits for our little chipsats so that they could develop their own code and their own experiments to run on these things on orbit. So we sent out about a dozen of these kits and actually had a couple of people develop interesting things. My favorite one came from a couple of guys in the UK who are members of a club called the British Interplanetary Society. They came up with the idea of writing pseudo-random data to the SRAM on the microcontroller and reading it back over and over again to check for bit flips. The idea being that you could repurpose the SRAM as a kind of coarse and cheap radiation sensor. By looking for radiation-induced bit flips, you could kind of repurpose it as a radiation sensor. So I loved that idea. I thought it was super clever. I found out years later that I think these guys had come up with it as an original idea, but it had actually been done back in the early 90s on a mission that went to the moon and successfully. So it's kind of very cool to learn about this. Okay, and one of the other things that we did as part of this effort was develop a very low cost sort of amateur ground station, so that people who backed the project and kind of sponsored their own satellite and had their own little messages transmitted from them could actually receive these signals themselves in their backyards with about $50 worth of hardware and a laptop computer with kind of a handheld ham radio antenna. So this was one of the more challenging engineering problems associated with this. You can imagine these little satellites. The transmit power out of them is about 10 milliwatts, and we're closing a link here from space at distances well over 1,000 kilometers. So not a lot of signal, and the signal to noise ratio here is pretty bad. To give you an idea of how bad, this is a plot of what the signal looks like coming out of one of these little satellites out of the radio. It's very clean, and you can basically read the bits right off of it on the scope, the bits being kind of where the phase flips here in the signal. This is what it looks like when you get it into the ground station receiver. It's totally buried in noise. In fact, on the ground, these signals are well below the noise floor. So they're basically invisible. We developed a whole bunch of kind of fancy signal processing tricks to pull these things out of the noise. I'll just kind of share one of them, which is kind of fun. It's called matched filtering. The idea is that we assign a unique ID code, kind of bit sequence, to each of these tiny satellites. The ground station receiver knows these ID codes a priori, and when it wants to listen to a particular satellite, it takes the incoming signal and performs essentially a sliding dot product against the ID code for that particular satellite. And if the signal from that satellite is actually there in the received signal, this dot product sort of produces a large output value and gives you a big spike out of the receiver corresponding to a bit. The idea here is that even if there's a lot of noise and a lot of, say, bit flips here, because you have this long ID code called a PRN code, you get a large effective gain from that, and it's tolerant to a lot of bit flips and a lot of noise. So we use this trick to both allow us to pick these signals out of a lot of noise and allow us to simultaneously receive signals from a lot of these little satellites on a single frequency band. These tricks are very similar to what's used by both GPS and cell phones. So we implemented, though, ourselves on these very kind of low-cost platforms with software-defined radio and a bunch of other interesting tricks. This is just a fun picture of some of the testing we did of this little scheme. This is my very patient wife, who I convinced to drive up a mountain for me and hold up our very scientific test rig of one of these little chipsats taped down to a piece of cardboard, held up to the sun. And I'm about 30 miles away down here in a park holding that handheld receiver I showed you with that laptop. And we added a whole bunch of attenuation in to the receiver chain to mimic the extra distance to space. And this is the output of that receiver showing a nice big spike above the noise. So this kind of indicates that we could successfully receive these signals under those kind of realistic link conditions with lots of margin. We got a chance to try this out on orbit a few years, about a year later. This was now, where are we now? It was about 2016, 2017 maybe. This is a German satellite called Max Valier that we got a sort of chance to piggyback on. Here's our little chipsat on a 3D printed mount stuck to the side of this larger satellite. I actually flew to Germany with these things in my carry-on and kind of went in the cleaning room, and we 3D printed this little mount and bolted it on there. I should mention that this satellite was completely independently powered on its own, our little chipsat. It only had a single electrical connection to the host spacecraft to allow for a kill switch, which was required per licensing regulatory requirements, so that we could shut the thing off in case of any interference. And we were able to successfully pull these signals down. This is a live image from the ground receiver, the first time we ever got these signals from space. These little stripes here are are actually these signals coming from the ChipSat on orbit from about 800 kilometers up. So the communication system worked. We got a chance to demo that on orbit. Switching gears and fast forwarding a bit more, one of the other problems we've looked a lot at that kind of is bootstrapped on these communications techniques is radio navigation among swarms of these kind of small satellites. It's a really interesting problem. It turns out that with these kind of receiver techniques that I mentioned, you can pretty easily also extract range measurements from the signals, right? So you can get sort of time of flight measurements, the amount of time it took the signal to travel from the transmitter to the receiver, and from there you can kind of multiply by the speed of light and extract a distance. So this works pretty well, and in fact, with the radio hardware that we have, we can get range measurements down to accuracies of below a meter, so pretty good, over hundreds of kilometers, say. So we've thought a bunch about trying to use this to do navigation among, say, small satellite swarms. The picture is kind of this, though. Say you know all the ranges here. There's a fundamental ambiguity because those range measurements, say, constrain the satellites to lie, in this case, 3 satellites to be on a triangle, right? I can arbitrarily translate and rotate that triangle. And so that ambiguity is just not resolvable given that only the range data. You need something else, right? There's a lot of ways to get that something else. One solution, say, is to have another spacecraft that has a known position that you can use as another reference point. This would be analogous to, say, having a GPS, right? Another way to go would be to have some ground station act as that known reference point. But we ultimately want to take these things into deep space away from Earth. And in this case, we're talking about doing this at the moon, perhaps, or an asteroid. And we don't have access to this kind of ground infrastructure or GPS, right, in deep space. So we've been looking at a really interesting third option, which is that in many cases in the solar system, actually, we have quite good gravity maps of these celestial bodies. This is a picture of one of these gravity maps of the moon. Turns out we have gravity maps down to a resolution of about 5 kilometers for the moon. Incredibly accurate. In fact, better than the ones we have of Earth. What you can think about doing here is, given this very lumpy gravity field and having access to a high accuracy map of that lumpy gravity field, you can look at these range measurements between the satellites. You can imagine as they're in orbit around the moon, say, as they approach an area where there's more mass and more gravity, the kind of lead satellite will speed up a little bit because there's more gravity. And then a little bit later, the next satellite will kind of catch up, right? And so this induces small variations in these range measurements that we can actually detect and measure over time over the orbit. And we can correlate those small changes in the ranges between the satellites with this gravity map and use it to figure out where we are over the planet. So sort of gravitational navigation. We're kind of working on this right now in collaboration with NASA Ames. And this is actually another mission we're flying that launched a couple of months ago called V-R3x, which is a bunch of these little 1U CubeSats. This is a picture of one of them. We have 3 of these on orbit doing basically what was depicted there around the Earth. We're collecting these range measurements and trying to demonstrate this kind of relative navigation technology. Okay, switching gears to another interesting problem that comes up on these very small satellites that we've been working on a whole bunch in my lab is how to actuate them. So we've kind of looked at this navigation problem. We've looked at the communication problem. We can talk to the satellites, they can talk to each other, and we think we have some ways of navigating them, given all these hardware constraints and these very low cost, sensors and radios we have. But they can't really do anything about where they are right now because we have no means of actuating them, of changing their either their attitude, their pointing or orientation, or their orbits. So this is a plot of the fraction of the spacecraft taken up by the actuators on traditional spacecraft. And this is specifically attitude control actuators. So these are the actuators that are used to reorient the satellite. So to say point an antenna at a ground station or point the solar arrays at the sun, this kind of rotational motion. These traditional actuators, there's a few different flavors of them. They're called momentum actuators, and they basically are big flywheels. You can imagine you spin the flywheel one way due to conservation of angular momentum, the body of the satellite will spin the opposite way to conserve total angular momentum of the system. This is a picture of one of these flywheel actuators. This is actually one from the International Space Station. This looks pretty big, but it's only, it's less than, say, 2 meters across. And keep in mind, the ISS is gigantic. It's the size of a couple of football fields across. So it turns out to actuate that entire massive structure in space, a couple of football fields, it only takes 4 of these flywheel actuators that are less than a couple of meters across. So as a fraction of the ISS, these actuators only take up about 0.2% of the total mass of the ISS, so tiny, tiny fraction. As we move down in the size of the spacecraft, though, we come to, say, a geosynchronous communication satellite, the sort of satellites that provide TV and satellite radio. These satellites are small in the ISS, but still very large. They're the size of commercial airliners, like the size of a 737, say. On those satellites, these actuators take up maybe 1% or 2% of the total spacecraft mass. As we move down further in the size scale, we get to something like a classic low Earth orbit imaging satellite, the kind of satellites that provide us with the image data I showed you before for agriculture applications, weather satellites, say. Those satellites, these actuators take up somewhere in the order of 5 to 10% of the total spacecraft. And those are typically, they range in size, but you can imagine these being the size of, say, a refrigerator. Now, as we move down further into this CubeSat regime, so now this is the size of that mothership satellite I showed you before, on the order of a few kilograms and, say, the size of a shoebox, roughly. At that size scale, the available actuation systems that you can buy commercially end up taking up anywhere from 1/3 to 1/2 of the spacecraft's total mass. So now we're talking about the spacecraft's mass and volume being actually dominated by the actuators, and it leaves very little room left once you have everything else you need to run the satellite, solar arrays, batteries, radios, flight computer. There's very little room left now for a payload to actually do anything useful on the satellite. So this is at this, CubeSat, few kilograms scale, and the trend is not encouraging. So if we talk now about pushing this farther down to the left on this plot to these very small platforms like the ChipSat at this sort of gram scale or even tens of grams, these sort of traditional actuation schemes just don't scale down. They're not going to work. They're totally not viable at this very small size scale. So we need other ways of doing it. This has been a really interesting area of research for us for the last couple of years. One option that we've looked at pretty in depth is something called magnetic torque coils. This is a really fun idea that's not novel to us, but has been around for a little bit, but we have a new twist on it. The idea here is to essentially turn the satellite into a compass needle, as I like to think about it. So the Earth has a magnetic field. This is sort of a cartoon drawing of it on the left. To sort of first order, it's a dipole, but it's actually substantially more complicated than that. It has a lot of fine structure, a lot of spatial variation as you move around the Earth, which will become important in a second. So given that magnetic field, what we do on the satellite is put electromagnetic coils on the satellite. And typically you would have, say, 3 of them oriented in XYZ axes on the body of the spacecraft so that you can produce an arbitrary magnetic moment vector on the satellite by driving the coils appropriately, by running current through these electromagnetic coils, right? And this produces a torque on the satellite due to the Lorentz force. This is kind of what this looks like, M cross B. So it's the magnetic moment due to the coils on your satellite, and we get to pick this M, right? By just driving these coils, driving current through the coils. And then B is the Earth's magnetic field coming from the environment that we have no control over. And this is the torque that gets applied to the spacecraft as a result. So we can produce any M we want, but it turns out we can't get any torque we want, which is unfortunate. The reason is because of this cross product. So what happens when you take the cross product, right, is that we can produce only torques perpendicular to B. We can never, no matter what M we generate, our coils on the satellite, we can never get a torque that's parallel to the B vector from the environment. So this is a problem. It makes controlling this hard because it's always what we call under-actuated. You only ever have control authority over 2 of the satellite's degrees of freedom, and not that 3rd degree of freedom. But the kind of magic trick that makes this work for us is that this B is changing. You can see the structure of this magnetic field is very complicated around the Earth, and we're moving around the Earth in orbit constantly. So as we move around the Earth in orbit, the direction of B is always changing. So once again, what we do here is we have a map of the Earth's magnetic field. We know what it is ahead of time. We carry around a map on the satellite, and we know where we are in our orbit. And importantly, we know where we're going to be, in the future, because the orbit's very deterministic, and we have good models of that. So we solve a planning problem where we look ahead along the orbit 4 or 5 minutes, predict where that B vector is going to be, and we solve a planning problem, a motion planning problem that says, given where the B vector is going to be over the next 4 or 5 minutes, I'm going to produce these torques when I can during that time window to get myself into a desired orientation by the end of the 4 or 5 minute horizon. And it turns out in low Earth orbit, given the variations in the magnetic field and what the orbits look like, we can basically get from any initial attitude to any desired final attitude. We can do kind of arbitrary large rotations of the satellite, arbitrary pointing and reorientation maneuvers in about 4 or 5 minutes from any orbit. So this is really interesting and kind of frees you up from the need for these momentum actuators. In fact, these coils can be produced right in the printed circuit board. The ones that we build now, we just make them as a trace in a multi-layer printed circuit board. So they take up basically no volume. And basically what the idea is to use clever software and clever algorithms to get away with these kind of cheap and limited actuators, right? So here's kind of a sped up image of actually doing this. You notice that this satellite, so this is executing, I think, a 90-degree slew maneuver. So you can get it to play again. Notice it does not take the direct sort of clean, what's called eigenaxis slewing motion from the initial to the final attitude. Instead, it does this complicated nodding motion. This is sped up. This actually takes about 4 minutes in real life, right? But it's getting this weird nodding motion because it's taking advantage of that time varying magnetic field vector. And I should mention, my lab kind of also specializes in this kind of embedded control stuff, and we've developed specialized solvers to solve this problem, which ends up essentially becoming a numerical optimization problem that we have to solve on board the satellites. We've developed custom embedded solvers to do this quickly on little tiny microcontrollers so that we can actually do it on these little satellites. Okay, so this is great. There is, though, a caveat to this scheme. Because we kind of only ever have a couple of degrees of freedom worth of control, and we never know what's going on perfectly, our maps of the magnetic field aren't perfect, and there's always environmental disturbances. This method is only good to maybe 5 degrees accuracy in pointing. So it doesn't get us that really fine pointing that we need for some applications. So another idea we've played around with is inspired by nature. These are kind of super fun videos. You may have heard of the falling cat problem. Cats always land on their feet. It turns out geckos are even better than cats at this. They can reorient their bodies by whipping their tails around. And in fact, they can perform full 3 degree of freedom, pitch, roll, yaw, attitude control by kind of wiggling their bodies and exploiting their tails. So this is also, very importantly, these guys, the gecko in this video is about 3 or 4 grams. It's right about on the same size scale as our chipsat. So there's kind of a really nice existence proof here that nature's figured out how to do this for us at the size scale we care about. Interestingly, just for fun, this idea has been kind of extensively explored dating back to the 1960s. This is actually video from experiments done on in the early days of the space shuttle program on the shuttle middeck of astronauts doing exactly the same thing. So people can do this too. You can kind of wiggle your arms and legs around in funky ways to reorient your body. And actually, it turned out NASA funded research in this in the early days of the space program. And they did these experiments on the ground using gymnasts, where they kind of had them bounce on a trampoline and gave them commands, turn left, turn right, et cetera, once they were already in the air, had them try these things out. And then, yeah, the experiments were eventually done in space. Kind of fun. So we've taken this sort of idea, the idea that if you have other degrees of freedom. Think of these as like tails or limbs, right, arms on the spacecraft that you can also do attitude control, again, without having these sort of classic flywheel actuators. The real advantage here is that by using some kind of appendage like a tail or an arm or a boom, you get a huge inertia advantage. So inertia, moment of inertia for a rotating body goes like ml squared, roughly, so length squared. So if you imagine a tiny little wheel buried inside the small satellite, the L is very tiny there, the length, the diameter of the wheel, say. Whereas if we have a boom that we deploy out of this little satellite, that L can be much, much bigger, and the advantage goes like length squared. So it's a huge win to put a boom out versus having a tiny wheel inside. So here's what this kind of looks like in simulation on something like that 3U satellite. Here we show 3 of these deployable boom actuators. And with this setup, because these booms, because they have large inertias and we can control them really precisely, we can actually do really fine pointing with this kind of setup. And we're currently exploring using actuators like this, these deployable booms, to replace reaction wheels on satellites at the CubeSat scale to enable astronomy. So imagine a CubeSat like this with a telescope. Doing this kind of thing would allow you to do ultra fine pointing to image things like exoplanets, where the objects you want to image are really dim and really far away, and you need to take really long exposures, which means you need very stable, very fine pointing over long periods of time, say minutes, to do these long exposures to image these dim objects. Okay, so now to kind of put all of this together, this is a video showing the completed KickSat spacecraft in my lab on an anti-static mat, all assembled, and just a fun video to show you what the deployment of this thing looks like in real time. I should mention as a disclaimer that in the final version, we actually tethered this top panel and the spring inside here to the mothership spacecraft due to regulatory requirements for not creating more space debris. I thought this was a little silly considering we were already deploying 100 plus of these little chipsats, but that was kind of the deal. And just in case you're wondering, the mechanism here at the top, in this top plate, there's basically a top plate. There's a conical spring that's compressed down in there, and a mechanism known as a burn wire that's very standard in these kind of aerospace applications, where we essentially have, in our case, being kind of low cost, it's essentially a piece of fishing line that's tied down to a heating element, and we run a large current through the heating element to burn or melt through the fishing line, and that's the release mechanism for this thing. The reason we do that, as opposed to, say, having a motor to actuate things like this, is that these burn wires are essentially totally solid state and ultra reliable. They basically can't fail, as opposed to motors, which have complicated, moving parts, and they can fail in vacuum and the kind of harsh thermal environment because of mostly because of the thermal effects, because things like greases don't do well in vacuum and wide temperature ranges. So okay, so that's the fully assembled spacecraft. This flew just about exactly 2 years ago now. Let's see. Yep. Next slide. Here's so I was lucky enough to get to go watch this launch. This was at NASA Wallops in Virginia. Turns out this is the closest you can get to a launch in the United States legally to watch a launch. So if you've never seen one of these, I really, really highly recommend it. If you're out in California, you can watch these things at Vandenberg. You can't get quite this close, but it's also a good show. It's an incredible experience to be up close to one of these. So this is the launch that we went up on. It was an ISS resupply mission. So there's a lot of these ISS resupply missions. They happen several times a year, and there's pretty frequent availability of rideshare opportunities on them. Thanks to NASA, they have a program called Educational Launch of Nanosatellites, or ALANA, and they award free launches to university projects like ours on these kind of things. So there's a lot of good opportunities to get rides to space for these kind of CubeSats. So this is our launch. This is a couple days later now. on orbit after the spacecraft went up and docked with the ISS and dropped supplies off. Basically, they went and dropped everything off at the ISS. Then I actually spent a couple of months docked with the ISS. They basically unload this Cygnus spacecraft. They unload all the supplies from it, and then they keep it docked to the ISS for a few months and essentially fill it up with trash. They fill it with all their garbage on the space station for a few months, and then once it's full, they undock it and they do a deorbit burn and push it down into the atmosphere where it burns up. What they did for us here was actually do two maneuvers after they undocked with ISS. They did a burn to lower the orbit of the Cygnus vehicle into a very low orbit, where just for us actually, so they could deploy our KickSat spacecraft. The reason they did this was due to regulatory debris and tracking concerns, because we were flinging out all these super tiny ChipSat spacecraft. This is basically the only way we could get permission from the federal government to do this. We had to be in a super low orbit where we could guarantee that our little ChipSats would burn up within a matter of days and not sort of stay in orbit for a long period of time due to concerns that they wouldn't be trackable because they're too small to see on radar. So it actually took quite a long time to get this launch to happen because of these concerns and the need for this additional maneuver that they did for us. So these are the last images ever captured of KickSat. This is it, getting flung out of the Cygnus vehicle in low Earth orbit. Pretty incredible videos that I'm super glad we were able to get. And shortly after this deployment, a couple days after this, we sent commands up from our ground station to that mothership satellite to trigger it to deploy all of our little ChipSats, similar to what you saw in that animation. Unfortunately, we don't have video of that. We didn't have any cameras on the CubeSat to capture images of that deployment. This is actually where we did this, where we commanded everything. This is the famous Stanford dish that's back behind Stanford University, where I was working at the time when we did this 2 years ago now. And there's a little shack down here that we're hanging out in. And this is a live plot of the waterfall plot of the receiver hooked up to this dish, showing you what we saw when we, right after we commanded this deployment and the ChipSats were released. All these yellow stripes here are signals from ChipSats. So we were able to get signals from a whole bunch of these guys and demonstrate that they were successfully deployed and that they could survive in orbit, or at least for a few days as free flyers, and that they could talk to each other. Actually, we did a little bit of a mesh networking demonstration, and that we could simultaneously talk to a large number of them using the kind of communications tricks that I mentioned before. So just to kind of wrap up a bit, a few more fun things that came out of this whole adventure that I'm particularly fond of. One is that we ran mission operations with a large community of amateurs around the world online through Google Groups. So we had this kind of Google Groups forum with ham radio operators and actually just people who got interested in the project, posting data as they received signals from the satellite from wherever they were in the world. We had people all over the place, South America, all over the US and Canada, people in Europe, people in Australia, posting packet data that they were pulling down here in this forum. So we had a bunch of amateur radio operators do that. I posted instructions for putting together that low-cost ground station that I showed you before with the kind of $50 worth of ham radio gear. We actually had one guy who'd never done any kind of amateur radio stuff take those instructions, put one of those things together and set it up in his backyard, and he pulled down some signals. So that was super fun. And then we also had a whole bunch of people who didn't know anything about space, didn't know anything about amateur radio, any of this stuff, who weren't necessarily super technical, who just got really into this, joined in the fun, and did things like analyze the data in Google Docs spreadsheets and make plots of like temperature and battery voltage measurements versus time. We had one guy who got really into the modeling the orbit mechanics of this whole thing himself, and was taking tracking data and predicting when the satellite was going to re-enter from current tracking data. And he actually did a better job at predicting our re-entry than NORAD did, the kind of official federal government agency does this kind of tracking stuff, which is super, super cool. So this was just a really awesome experience. And for me, kind of in many ways, the whole point, of dramatically reducing the cost of all of this stuff and broadening participation in spaceflight and getting sort of average people involved in this stuff in a way that's really historically not possible when it's super expensive to put things in space. And it's sort of classically, we think of this as the realm of only defense and government contractors and people like that. So this was super fun. And a quick plug, all of the stuff that I've shown you is all open source. And in particular, so the chipsets are, but also the avionics for the CubeSat. And in fact, the whole design for this CubeSat has been open source. We've kind of spun this out as another project that we call PyCubed. This is the main avionics board for the CubeSat. And we've now flown this on several other missions, in particular that V-R3x mission that I showed you where we're doing the navigation experiments. That's also running the same avionics. So we've basically stress tested these a bunch of times, redesigned them a few times, had a lot of lessons learned over several missions now. These have been radiation tested, all the good stuff. So they're pretty reliable. And we've designed them to be super easy to use and fabricate and fairly low cost. And maybe most importantly, we've set these things up so that they run Python, which is a huge boon for educational outreach and getting these in the hands of undergraduate students and getting more people involved in this kind of stuff. It really, really lowers the barriers to entry because classically, programming something like this would be embedded C code and a lot of kind of low-level assembly kind of stuff to program microcontrollers. And having it run Python just really lowers the barriers to entry and makes it way easier for people to get involved, and also makes software development for these kind of platforms a lot less error prone and eliminates a lot of bugs and is just safer. One of the other interesting side benefits of this is that we can actually upload new code to the satellite really easily because it's just running Python in an interpreter. You can actually just upload .py files, just text files, Python files to the satellite and instruct the satellite to do new things, kind of give it new capabilities, all this kind of stuff from the ground. We've gotten these, a whole bunch of other universities are now using these. I taught a capstone class around these right before the pandemic kicked in. And yeah, we're trying to get these out there in the hands of lots of students. And yeah, finally, just the whole thing is open source, as I mentioned. If you're interested in any of this stuff, hardware designs, PCBs, code, everything's online, everything's on GitHub, and you can check it out. You can build your own and get involved. We'd love to have you, love to hear from people who are interested in standing up this kind of stuff and getting involved. And finally, just a teaser for, it was mentioned in my intro that I'm on the advisory committee for this project, Breakthrough Starshots. This is kind of way off crazy in the future applications for these sort of very tiny satellites. The idea behind the Breakthrough Starshot project is to try to send a spacecraft to our nearest neighboring solar system, Alpha Centauri, which is 4 light years away, by taking something like our little ChipSat, a gram scale satellite, attaching it to a solar sail like this, and then shooting with a giant ground-based laser to accelerate it to really high speeds so that it could make it to Alpha Centauri in maybe 20 or 30 years. Fun project. And finally, I'd love to like to thank my graduate students who do a lot of the hard work here, who really put in the time to make all this stuff happen, and a lot of other people who've helped out on this stuff over the years in various ways. And with that, I'd love to open it up for questions. This is my contact info, my lab's website, or GitHub, where you can find all our more information on all this stuff.